Good afternoon. This presentation has been made by Matthew Mancini and Keanu Dugan, and this is our senior engineering project, a Bluetooth barbell motion tracker. The goal of this project is to design a low-cost, durable device that can be attached to a barbell and measure acceleration, velocity, displacement, and power in real time. This will support athletes, coaches, and strength departments by providing useful performance data without the high cost or fragile components of current systems. The main problem we're addressing is that most barbell tracking systems today are expensive, fragile, or provide limited measurements. Our project aims to produce a clamp-on Bluetooth device that measures all major kinematic variables such as displacement, velocity, acceleration, and power. We also set a strict cost requirement. The device must stay under about $400, and our current projected cost is only around $120. The real benefit is giving athletes and coaches real data to evaluate technique, monitor fatigue, and reduce injury risk. To validate our ideas, we studied existing research. First, the Abbott IMU versus 3D MO cap. Study showed that the IMUs can be just as accurate as full motion capturing systems, so using a small accelerometer is a valid approach. Clement's systematic review also confirmed IMUs are reliable for barbell velocity tracking. Brooks demonstrated a collar-mounted IMU system with 99.5% tracking accuracy, which aligns closely with our design. And Gonzalez-Alonso showed that low-cost custom IMUs can actually outperform expensive commercial systems. So overall, our design direction is strongly supported by existing research. Here is the system overview of our design. The clamp on the barbell collects raw accelerometer data. That data goes to the Arduino, which processes the signal and sends them over Bluetooth. A base station on the ground receives the data and sends it to a PC for live visualization and analysis. Everything is wireless, which eliminates the biggest failure point of old systems, the physical tether. So for our expected results and the progress we have so far, we expect the device to collect accurate acceleration data and calculate velocity, displacement, and eventually power. Right now, our CAD models are complete and the mechanical design is ready for 3D printing. The system uses an Arduino Nano 33 BLE Sense Rev 2 paired with a GY 521 accelerometer. Power will come from either a 9-volt battery or a 3.7-volt lithium-ion battery, depending on heat testing. We're also designing the attachments so the clamp is secure and doesn't shift during lifts. Here is the clamping design in more detail. It's designed on On-Shape and mounts near the weight plate. It houses the Arduino, the accelerometer, and the battery. A flathead screw secures it tightly to the bar. The full mass with the 9-volt battery and the Arduino Uno is about 1.116 pounds. The full mass with the 3.7-volt LiPo battery is about 1.03 pounds. This weight imbalance means we will add a matching counterweight on the opposite side to keep the bar balanced. Here are some of the additional components we've integrated. The counterweight ensures that the bar doesn't tilt or rotate due to the clamp's mass. We designed a trapdoor for easy access to the battery in the Arduino, which will be shown on the next slide. The main screw mechanism that screws into the hole shown on the top of the clamp clamps the device firmly in place so that it doesn't slide during a movement. Here are some pictures that will be continued from the previous slide. These images show the clamp add-ons and concepts in more detail. We will use PLA for the initial prototypes because it's inexpensive and easy to print. The goal here is to verify form fit, screw alignment, and internal component spacing before printing with strong materials if needed. Our next step is to print and test the clamp under different movement conditions.
So here's a breakdown of how the electrical design works and what's happening in the system. Everything starts when the user presses the push button. That button then will send a high signal to the Arduino, which basically wakes up the system. Once the Arduino receives that high value, it powers on fully and begins to initialize all of the necessary components. That includes the controller itself, the I2C communication for the accelerometer, and the Bluetooth module. This is also where we calibrate our sensor offsets, so the readings are accurate. After the initialization is complete, the Arduino begins gathering data from the accelerometer. This is where we collect the movement information used to calculate speed, force, and power. Next, all of that data is transmitted through the Bluetooth module. A paired device, typically a phone or a computer, will receive the data in real time. Depending on the setup, we can also pass this data into the Python script to turn into visual analytics, like graphs or performance summaries, if this is applicable for our time frame. Overall, the system is designed to be simple for the user. One button press activates the entire measurement and the communication process. On this slide, we will be explaining how the data moves through the system, starting from the clamp all the way to the computer. On the clamp side, we have the Arduino, the accelerometer, and the battery. The Arduino continuously collects acceleration data during the lift. Inside the clamp, the Arduino is connected to transceiver number 1. First transceiver is responsible for sending the data wirelessly. So, as the Arduino gathers acceleration data, transceiver number 1 immediately transmits it to the base station side. Now on the base side, which sits on the ground, we have transceiver number 2. Transceiver number 2 receives the wireless data coming from transceiver number 1 in real time. From there, transceiver number 2 is connected to a PC using either Ethernet or USB, depending on the setup, or another wireless Bluetooth connection if the time will allow. Once the data reaches the PC, the computer processes it and can run calculations, generate graphs, or display performance metrics. Now let's look at what happens once the PC receives the data. This is where all the processing and calculations take place. The accelerometer gives us raw acceleration values. From that, we can calculate velocity and displacement using numerical integration. To calculate velocity, we'll use the trapezoidal method. The formula is velocity initial plus 1 is equal to velocity initial plus acceleration initial plus 1 divided by 2 times the change over time. This lets us estimate how the velocity changes over a small time interval. We apply the same trapezoidal approach for displacement. This helps us track how far the object moved during the lift. Once we have acceleration, we can compute the force. Force is just mass multiplied by the total acceleration, and that includes gravitational acceleration. Finally, power is calculated using the standard physics relationship, power equals force times velocity. This tells us how explosive and efficient the user is lifting. We will also have visualization if the time will allow. For real-time plotting, we can use a serial plotter that's built into the Arduino IDE, or we can transfer the data into Python and visualize it using libraries like matplotlib or scipy for more professional graphs and analytics. This slide shows the pseudocode that represents the full logic flow of our system. It outlines what the Arduino is doing behind the scenes as it collects data, detects a lift, processes movement, and sends results back through Bluetooth. In the setup phase, the Arduino initializes all communication channels: serial for debugging, Bluetooth for wireless data transfer, and I2C for communication with the accelerometer. The NPU 6050 sensor, or GY521, is then initialized and we can run the calibration step. This computes the bias values for each axis so the readings are accurate. We can also define our sampling interval, in this case every 10 milliseconds, which gives us a 100 Hz sampling rate. Once the setup is complete, the system waits for a start command. This can come through a Bluetooth app or a physical push button. We are planning on using the physical push button. Before each new measurement, we reset all integration variables like velocity and displacement. Then the system enters the monitoring state. In this state, it continuously reads acceleration data, subtracts the calibrated biases, and projects the acceleration onto the axis of the lift. We also apply a low-pass filter to clean up noise and ensure smoother data. While monitoring, the system checks whether the filtered acceleration crosses a threshold that indicates the beginning of a lift. When that condition is met, we record the start time and switch to the in-lift state. During the lift, we integrate acceleration to compute velocity and displacement in real time. The code keeps checking for a stop condition, usually when the acceleration drops or stabilizes, indicating the lift is finished. When the stop condition is detected, we record the end time and compute all final results, things like velocity, peak force, and power. These results are then sent over Bluetooth to the paired device. After finishing a lift, The system checks if the user wants to repeat the process. If yes, it then returns to the monitoring state, waits for the next lift, and if not, it will return to idle. Throughout the code, ensures consistent sampling by delaying until the next scheduled interval. This flowchart walks through the full sequence of how our system operates from start to finish. We begin at the start block, and the first thing the system does is initialize all values during setup. This includes calibrating the sensors so that we're starting with accurate readings. Next, the system prompts the user with a message, asking them to enter the weight being lifted in pounds. Once the user enters the weight, the system waits for person 2 to press the physical button on the device to officially begin the measurement process. When the button is pressed, the system resets all timers. Velocity and displacement variables and the internal flag state are also reset. It then begins reading accelerometer values and starts looking for any movement that resembles the beginning of the lift. At this stage, the data is filtered or smoothed using a low-pass or high-pass filter to remove the noise. The system continuously checks whether the user is attempting a rep. If not, it loops back and continues monitoring the accelerometer. Once lift behavior is detected, we record the start time and change the system flag to in lift. During the lift, now the system continuously reads accelerometer data as the rep occurs. It applies the physics equations to calculate velocity, displacement, and power in real time. We must also run additional loops to determine metrics like peak and average velocity. The system checks repeatedly to determine when the lift is finished. If it detects that the motion has ended, it moves forward to calculations. It computes lift speed, which involves integrating the acceleration data over time. The system prepares the final results: velocity, power, displacement, timing, and performance metrics. These results are then transmitted via Bluetooth using the HC05, HC06 modules, or the Nano with BLE. After that, the button state is reset, and the system checks whether the user wants to perform another rep. If yes, we loop back to the beginning of the measurement process, and if not, the system moves to the end state. This slide shows the current code we're using to work with the GY521, which contains the MPU6050 accelerometer and gyroscope. Right now, the code initializes the sensor, reads the raw acceleration data, and maps them into simple 0 to 1023 range. This is useful for basic visualization, but not for real physics calculations. We start by including the wire, I2C dev, and the MPU6050 libraries, and create an MPU6050 object to communicate with the chip. During setup, we begin serial communications, initialize I2C, and wake up the MPU6050. We can also check that the sensor is properly connected. In the loop, we read accelerometer and gyroscope values using getMotion6, which gives us raw integer readings for each axis. After that, we map those raw values into the 0 to 1023 range so that they behave more like analog inputs. Then we print them to serial monitor. The next step is to convert those raw values into meaningful units, specifically acceleration in Gs or meters per second squared. The MPU6050 outputs acceleration as a raw 16-bit value, and depending on the sensitivity setting, we can convert it using the datasheet scale factor. For example, at the default plus or minus 2G setting, 1G is equal to about 16,384 raw units. So acceleration in Gs is simply the raw reading divided by 16,384. This conversion allows us to plug the data into our velocity, displacement, force, and power equations accurately.
Our mechanical designs are nearly ready for manufacturing. All CAD models are finalized and components have been ordered. Our main risk includes heat inside the clamp, mounting failure, and difficulty printing the screw mechanism. To mitigate these, we may switch to a cooler 3.7 volt lithium-ion battery, redesign or strengthen the clamp, and if needed, use a store-bought screw instead of a 3D printed one.
Here's where our project currently stands. On the software side of things, we're now in the testing and validation phase. This means the core logic is written, and we're focused on making sure the data we collect is stable, repeatable, and accurate. All the major hardware components are already acquired: the Arduino Nano, GY521 accelerometer, and the Bluetooth transceivers. So we have everything we need to complete the full system. The next big step is physical integration, wiring everything together into one unified system. This includes ensuring the power routing, sensor orientation, and communication lines are all correct. Now let's go over the primary risks and how we plan to mitigate them. Our number one risk is the Bluetooth signal interference or range issues. The risk of unreliable Bluetooth communication, either due to interference or limited range. To address this, we plan to run controlled distance and interference tests, This lets us identify the minimum and maximum reliable distances and adjust module placements or signal settings as needed. Software integration problems. Another risk is unexpected software behavior once all modules are combined. This is common when multiple systems start interacting. We're mitigating this by refining and debugging the firmware with help from external references like Arduino documentation, sensor data sheets, and manufacturing examples. A final risk is needing more advanced analytical tools once the data grows in complexity. To address this, we're researching compatible formats for transferring data like CSV or serial logs, and exploring Python libraries such as NumPy, Pandas, Matplotlib, and SciPy for future visualization.
Here is our manufacturing plan. Mechanically, the clamp and counterweight will be 3D printed by January 30th, 2026. Electrically, soldering and wiring the accelerometer, Arduino, and battery will also be completed by January 30th, 2026. Software development will continue in parallel with the goal of completing Bluetooth transmission and kinematic calculations before the end of January so full integration testing can start.
Slide, we're focusing on the testing plan for the integrated sensor and Bluetooth pipeline. Essentially, how we ensure the data collected by the accelerometer is reliably transmitted and usable. First, we test the full end-to-end pipeline during dynamic motion. This means making small lifts, rotation, and shaking motions while observing the transmitted data. The goal is to confirm that the readings we see on the receiving device reflect the actual movements, and that the start and stop detection logic triggers at the right moments. The success criteria here are straightforward. The pipeline should behave consistently in real-world motion without drops or erratic values. Next, we focus specifically on the Bluetooth connection. We test pairing and connection reliability with multiple devices, like PCs or phones, using the HC05, HC06 modules, or the Nano BLE. It's important that the receiving serial monitor displays accurate synchronized data in real time. Success is achieved when the system streams data reliably with minimal packet loss and no interruptions during a measurement session. Finally, we verify the accelerometer itself produces stable, repeatable readings. This includes checking all three axes, X, Y, and Z, against expected stationary values. For example, when upright, Z should read roughly 9.81 meters per second squared. We also perform calibration routines to remove sensor biases. Success criteria. The success criteria for this one is going to be our sensor output matches expected gravitational and motion values with an acceptable tolerance, ensuring reliable data for the rest of the system. By combining these tests, we ensure that the back-end system from sensor to Bluetooth to receiving device is accurate, consistent, and ready for further processing and visualization.
This slide shows our testing plan. So this slide outlines our subsystem level testing approach with clear pass-fail criteria. For mechanical testing, the goal is to confirm the clamp stays secure under vibration and simulated lifts. For electrical testing, we check that the accelerometer provides stable, low noise data at the expected sample rate. For software testing, we verify that known acceleration inputs produce correct velocity and displacement calculations. After each subsystem passes individually, we'll run end-to-end tests to ensure Bluetooth transmission and kinematic outputs work together. This slide shows our project schedule, which follows the Monday timeline linked in the presentation. Dr. Knight also has access to this link via an email invite that has been accepted on his end. Mechanical printing, prototypes, electrical integration, and core software blocks are all planned to be completed by February 16th, 2026. After that, February through April is reserved for full integration and testing, both subsystem and end-to-end trials. The remainder of the summer is for refinement, expanded testing, visualization tools, and documentation. We are on track with the timeline and have built in contingency time for redesigns or debugging. This slide shows our total project budget, which comes to $119, well under the original $400 requirement. The main costs are the Arduino Nano 33 BLE cents at $40 and the nylon filament for 3D printing at $50. Our accelerometers and LiPo batteries were inexpensive, costing about $5 for the sensors and $8 to $11 for the battery setup. Overall, we've kept the design affordable while still using reliable, well-supported components.
In conclusion, we have very high confidence in our system. The design is based on validated research, and our planned approach addresses the core challenges. The project is on track. The only reasonable showstoppers that we have are the Bluetooth reliability, data being transmitted in a noisy environment, and any sensor drift, where the accelerometer may be knocked or moved within the device, and the velocity and displacement calculation may be affected over time.